Welcome everyone to the EasyPower Tuesday Refresher Series. My name is Jim Chastain, and our topic today is the result of reviewing dozens of arc flash studies from beginners and veterans alike through the year, and realizing there was a list developing of repeated mistakes, and I wanted to share those with the group in hopes of expanding your awareness. Sometimes it's because standards have changed, sometimes the errors because of lack of knowledge of the tools, and other times it was just a beginner trying to get traction on the whole topic. So welcome to all. Appreciate your attendance today. As we are in the habit of doing, I'd like to start with a couple poll questions just to get some feedback on where people stand in this topic. No obligation and certainly no liability. First question is, what is your experience regarding arc flash hazard assessment? And if you would please just kind of indicate what applies to you. So it looks like we're close to a quorum. Let's give this another 5 seconds. Outstanding. So here's how folks have responded to the first poll question. Looks like we've got a fairly diverse audience, and that's very good. Second question is, what is your preferred option? And I'll give you a list of options. And again, these apply differently to different members of the audience, so it's just your perspective or your opinion, frankly. And here's how folks have weighed in. Excellent. Well, good. And then finally, which element carries the most weight in deciding whether to outsource or not? All right. Here's how folks have weighed in on this question. Excellent. Well, again, thank you all for attending, and let's jump into my list. So these are the list of top 10 mistakes, and 3 or 4 of them fall into a beginner category. A couple are due to the change in the standards, and a couple others are some nuances that may arise if you're using the tools for the first time or not used to some of the specifics. So the first on my list is what I refer to as the arc flash paradox, and it's a term I came up with to describe the counterintuitive nature of arc flash itself, and it applies to frankly all beginners, and it's not understood by many, even PEs who may have not done a study themselves. I personally discovered it on a phone conversation soon after I joined EasyPower. Got a call from an electrician in Oklahoma. He said, Jim, I think there's a problem in your tools. I just purchased EasyPower. And so as he described his one-line diagram, I drew it on the screen and shared it with him. And the conversation went something like this. He said he had the responsibility of labeling the above-ground distribution system for an oil field there in Oklahoma. And he said he's looked at all the elements in the system. So we start with the first cable here on the left. And he said the cable is single conductor per phase. It's a 1C cable. It's an outdoor run, so it's THWN. It's 50 feet long. And he noticed that now that we have auto-calculate, it's automatically calculating the impedance of, in this case, a 350 kcmil cable routed through a conduit. He said that all makes sense. He says the second cable is the same as the first, so I'm going to right-click and copy the first one, right-click and paste to the second one, and then open up the dialog box, and sure enough, the data has been transferred over. He said the second cable is the same construction, but it's 1,000 feet instead of 50 feet. So we're going to put in 1,000. We notice that with on auto calculate, nothing changes here for a number of reasons. And he said he looked at the nameplate on the transformer, and he said the transformer nameplate has data that can be shared with EasyPower. That it's an oil-filled transformer, class OA, which means it doesn't have forced air. It works with a fixed 65-degree rise. The kVA rating on the nameplate was 1,000 kVA. And the impedance, which is on the second tab here, is 5.75%. Now, the X over R ratio and the zero sequence ratio may not be on the nameplate, but the tool will calculate those. And then when it comes time to coordinate the protective devices protecting the transformer, then all this TCC plots are in line with ANSI C57.109. Now, the reason I like this example as much as I do, he said he had only one protective device in his system, and it was this fuse in the electrical cutout switch. He said he had opened up the switch and looked at the label on the fuse. He said EasyPower has a device library with over 40,000 entries, and so it's important to get the part number for any protective device entered in the database. He said he looked at the label and it's an AB chance fuse link. So as he told this to me, I was filling in the blanks, that the model was a Model T, and we both chuckled because we thought of Model Ts in a different context, and the size was a size 12. Now I want to make sure that the tool has found this in the device library, so I want to hit calculate and see one or both of these numbers change. The fact that this came back with a 15, the tool is saying, Jim, I found the part number you gave me in the device library. The manufacturer tested it to an ANSI standard using symmetrical current, and the X over R at the test fixture was 15. The reason that's important is EasyPower is going to calculate the X over R at every bus and then compensate for any difference between the power factor in the test vehicle versus the applications in the system. So once we've got the part numbers and the data fleshed out, we're ready to go to short circuit focus. We get a clean one-line diagram and a set of icons here at the top. He said we want to look at a half cycle. I'm on the top row. Half cycle, three-phase bolted fault, and then we're going to fault all the buses. And we get a bunch of numbers and some pretty colors. Now we're only looking at the A phase as indicated by the icons up here. Because this is a bolted fault, we're simulating all three phases bolted together, so the magnitudes will be equal. He said this makes sense. If I have a three-phase bolted fault in the secondary of the transformer, each phase will see 20,915 amps. If I walk over here to this panel 50 feet away, I have a three-phase bolted fault. Each phase will see 17,878. And if I walk to this panel 1,000 feet away, I'll see a bolted fault phase magnitude of 4,351 amps. He said that makes sense. Now we're ready to do the arc flash calculations. The arc flash icon in EasyPower Tools is this little Burning Man symbol on the top row. And once I invoke that, we get new calculations and new numbers. And he said, Jim, this is where I have a problem with your tools. I said, Vern, I don't get your point. What are you trying to say? He says, right here on the secondary of the transformer, I see the arc flash boundary is just under 26 inches. The incident energy is 2.1 calories per square centimeter at a working distance of 18 inches. So I know I can work on this bus safely with a 4-calorie PPE. If I walk down to this bus 50 feet away, just over 27-inch arc flash boundary, 2.3 calories per square centimeter at a working distance of 18 inches. So I know I should be able to be protected wearing a 4-calorie PPE to work on this bus. But if I walk to this bus 1,000 feet away, the arc flash boundary is almost 59 inches, and the incident energy is 8 calories per square centimeter at a working distance of 18 inches. And now I need to put on more PPE to be protected. What's wrong with your tools? I said, I don't get your point. What are you trying to say? He said, Jim, I've been an electrician for 25 years, and anybody that works in electricity knows the farther away you get from your energy source, the lower the energy is going to be. You're telling me that energy goes up. How can that be? Well, my response was, you know, I've been an electrical engineer for 25 years, and I agree with you. I don't see how the energy can be going up. Well, the reason for the anecdote, and it was a true story, a true conversation, is to show the value of the tools. Because at every juncture where you do an arc flash calculation, you want to verify how the calculations are being made or the equations are being followed. And to do that, I'm going to use the arrange for arc flash icon here at the top and then look at each bus. If we look at bus 2, it's a 480 volt bus. The protective device is the fuse. As we described it, it's got this dimension and this gap, air gap. And we know the bolted fault current. According to the IEEE model, the maximum arcing current will be 14,018 amps. According to the datasheet for that fuse, it'll take 64 milliseconds to clear the arc. And that's where in the IEEE equations, we get 2.1 calories per square centimeter. We walk down to bus 3, 50 feet away, still 480 volts, still the same fuse, still the same air gap and enclosure dimension. Now the arcing fault current is going to be 12,060 amps. According to the data sheet, it'll take 82 milliseconds to clear the arc. And that's where we get the 27-inch arc flash boundary from the 2.3 calories per square centimeter. If we walk 1,000 feet away, it's still 480 volts. It's still the same fuse, still the same electrode configuration, enclosure dimensions, and electrode gap. But now the maximum arcing current is 2,803 amps. According to the data sheet for that fuse, it will take almost a second and a half to clear the arc. And consequently, if I'm wearing the 4-calorie PPE that I used when I was working on the transformer secondary, and I come down here, I'm going to select these and compare these two results. And come down here, and with my 4-calorie PPE and accidentally induce an arcing fault, my exposure to the arc will be greater than my PPE rating, and I may not be in a safe condition if I were under those circumstances. And so both the electrician and I went, duh, I get it. Time is everything when it comes to arc flash. So the arc flash paradox tells us that within the same system, you can have buses with high incident energy, with low current, and or with high current. It depends on the time it takes to clear the arc. So I reiterate, time is everything when it comes to arc flash. You can't just look at a piece of equipment and tell whether it's an arc flash hazard or not. Now, 25 years ago, a design like that, like he described, was perfectly fine because arc flash wasn't something that was taken into account. Today's, and the problem was that we had fuse protection or the overcurrent protection in the primary side, and the current that was being measured at the arc was not being extinguished fast enough to prevent arc flash hazard or arc flash damage. So today, the solution would be to properly size protective devices for each of the loads on the secondary side. Number 2, using the infinite source when no utility is available is the mistake. And the problem is it's not a bad assumption if you want to test equipment duty, but it's not a good idea when you want to test arc flash incident energy. So here I'm comparing two different utility sources. One is an infinite source, which is very high current availability, against what's more of a typical load on a utility system. And we see on identical subsystems, or identical facilities, that we do have a little bit higher infinite bus current available on the main distribution board, comparing the realistic fault data to the infinite bus. But just as before, when we look at the arc flash results, we get a higher result on the lower current, again, because we have the primary protection on the high line side of the transformer. So it's not necessarily a good idea just to assume an infinite source is the best stake in the ground when I'm looking at arc flash calculations. An alternative, when you don't have access to utility data, is to make an assumption based upon available information. This could be what your neighbor facilities are recording, the distance from the substation, the size of the utility service equipment, the size of the breaker that's being used. Create two scenarios, one with an available utility current that's 10% higher and then 10% lower than that starting point that you've assumed, and then go with a more, as you do a comparison, go with a more conservative result. And above all, you want to make sure you discuss this procedure and the assumptions that you're making that you've documented with the facility owner, so he knows that going forward it may be something that needs to be corrected. The third mistake is thinking that all buses are created equal. In the early 80s, when Ralph Lee proposed that there is a hazard that can be identified other than electroshock, it was something that was a different way of thinking about safety, electrical safety. And it wasn't until 2002 when some sort of testing database has been developed, which was the resulted in the IEEE 1584 guide for performing arc flash calculations. And the model parameters that are included voltage, bolted fault current, working distance, reduced arcing current, air gap, enclosure, or open air situation, and then the arc time. But it also included the standard consciously included conservative approach and guard banding at several different intersections, because there were still a lot of unknowns in the database that weren't being handled. So it wasn't until 2018 that the 1584 was expanded and updated. And at that point, it was recognized that there is a difference between things like an open air installation versus switchgear or panel boards. And so the new model adds enclosure dimensions, electrode configuration, and it's less conservative as far as its recommendations and matches the test data better with the expanded testing that had been done. So that's number 3. Number 4 is confusing PPE with label on the label and the PPE for hot work. I think it was in Stockton that we were doing an arc flash workshop, and an electrician raised his hand and said, "Jim, why not put 6 inches working distance on the label instead of 18 inches? I mean, when I'm working on it, I have my hand is within 6 inches of the bus work." And my response was, do labels authorize hot work? And clearly they don't. The working distance on the label is typically the distance from the head and thorax to the bus, the arc hazard, while removing the cover. It really doesn't give us any indication of what it takes to work on the equipment. It's just a convenient number to calculate instant energy for the label. So to look at an example of this, let me kind of close this guy out. And so the issue is, how does this impact and where does it come up as far as making information available to people working on the equipment? And that's the function of the work permit. So here we have some typical loads, and I just want to show you the differences between a small junction box. If I look at the database, and the dialog box shows that we've identified this as a small junction box, that the arc flash hazard, if you take the default measurements from the standard, it has the working distance is standard of 18 inches, electrode gap is 13 millimeter. It's typically described as a vertical in a closed box, and it's got a very small box dimension. Well, if we look at the same thing for a safety switch, this is not in the standard. It's actually something that EasyPower puts in the typical values based upon industry typicals. And specifically, if we look at square D dimensions, we have a working distance of 18 inches, a 32 millimeter gap, user specified. When I look at a picture of a square D safety switch, the bus work is pointing straight at me, especially if the fuse is blown. Now, there is a plastic cover, but that doesn't dissuade an arc if it's bound and determined to open up. And then the typical values for, so you'll notice in EasyPower, we can either use the typical value or a user specified value, which I'm doing here, and we'll see the result when we do the instant energy calculation. So the point being, if I'm going to compare these three, go to fault the buses, and we see there's a little bit of a difference, the worst being my horizontal orientation, and the rest being well below a 1 calorie or 1.2 calorie guideline. So the question is, what's the worry? Well, the worry is if I'm going to work on this bus, let's say this open safety switch, and I haven't disabled it from the feeder, am I in a safe condition, and what should my PPE be? Well, in EasyPower, I want to develop a work permit. I guess I need to select a single bus. Develop a work permit to remove or install fuses. Let's say I know for a fact to be able to do that, I'm going to be within 5 inches of the voltage if I haven't disabled it. And so the work permit that's developed shows me both. If we look over here, it shows me the restricted approach and the limited approach boundaries. It shows me the arc flash boundary and the arc flash boundary of 10 inches, but it shows me that I need to have 4.8 calorie protection at a distance of 5 inches. And so this should be something that I'm aware of if I'm going to go out there and replace the fuses. And if this is uncomfortable, then I may want to consider changing the procedure to isolate that fixture even further. So the point being that the point being is that what's on the label doesn't necessarily mean that's safe condition for doing any kind of work inside the equipment after the cover's off. And that surprisingly happens a lot. So hot work permit should provide details, working distance, PPE, and tools for a specified task, and they can be different for whatever task I'm going to do. And so that's the reason that EasyPower can develop my work permit for me. Rule number 5, frequently I receive studies where people have used the 2-second rule on all voltage levels, and frankly 1584 describes it as something that can be applied to all voltage levels, but it's not exactly approved. And if you paraphrase it, 1584-2018 says, if an instant energy is high due to long tripping times of the overcurrent protective devices. Now the inference here is I have low current, which means I'm getting long trip times, and then the worker has room to escape if necessary. It may be reasonable to limit the instant energy calculation to 2 times. But in not so bold print, it says to use engineering judgment in any case. Well, the reason I have an issue with this is that there's evidence that 2 seconds may not give me a true picture of the hazard that's being analyzed. And so frankly, I would not utilize a 2-second protection on anything but less than 250 volts. So here's Here's a study that I was sent. And if we look at short circuit and see how things were set up under short circuit. So this doesn't have 2 seconds set up, and I want to verify that it's okay to do so. And I want to look at this particular bus down here. So let's go ahead and calculate the instant energy, fault the bus. Now, for some strange reason, we get 9,000 calories, and that's very high instant energy. I'm not going to look at the current yet. I'm just going to go apply 2 second, see if that's a valid, and it's 480 volts. At least this is the way the conversation went. And by doing so, applying this 2 second rule, I get a more civil 20-inch arc flash, 20 calorie per square centimeter. If I compare that to these other buses, they fall into the same range, which is civil, but is it correct? And the problem that I have with doing this as a first step and limiting the calculation time, there's a potential obscuring miscoordination, which is not necessarily the case here. But what is potentially the problem is that we could have a poorly set up protective device. If we go to coordination, we plot this particular feeder leg, and we take off that downstream breaker because we're not really looking at it, we see that we have the relay set up to protect the transformer damage curve, which is nice, but it's because of this time delay that we're getting high instant energy. So just out of curiosity, I want to invoke Smart PDC to see if it has a better recommendation. And I can see that Smart PD suggests we lower the protective device, the trips delay on the relay, such that we have better protection for the transformer, and we still have coordination for the downstream load. And where that leaves us with instant energy is an even lower 13.7 calories per square centimeter. So the point I would make is the 2 second rule doesn't even come into play here if we properly coordinated or set up the protection for the transformer. And not overly critical and not even and frankly, I would only use the 2 second rule on less than 250 volts because it can obscure coordination and protective devices. Mistake number 6, neglecting to check the overcurrent protective device coordination, assuming nothing has changed when you update the system. Well, you may be correct. If we did a protective device coordination study when we originally commissioned the system and nothing's been changed, then it should still be good. But have any fuses been swapped and for some reason not documented, or even have different values in the different phases? Or has someone tweaked relay settings or low voltage power circuit breaker settings without understanding that could change our not only our coordination, but it could change our instant energy or equipment protection? So what I suggest is, rather than taking this as a first step to ignore or assume nothing has changed, do at least a sequence of events check. And in EasyPower, it looks something like this. Let's go back to so sequence of events is a feature that's part of EasyPower coordination module, and it allows me to do the following. If I go to coordination, which is this icon up here on the left or right side, pick a downstream load, look at current, and fault that bus, I can see the contribution current from upstream and then the total available fault current on that bus. But I can also see the sequence of events icon on the second row. And once I invoke that, the tool shows me what the tripping order is for every upstream device if this bus faults. So if this main motor control center faults, this breaker trips in 190 milliseconds, this breaker trips in 35 seconds, this fuse trips in 33 seconds, and this relay would have tripped in 300 milliseconds, and they're flagged red because they're potentially miscoordinated. Well, you might say, well, that's good information, Jim. Can you give me a report? If I go to PDC options and check create a sequence of events report and come back and fault that particular bus, then in addition to my one-line display, I get a sequence of events report that tells me that same information in tabular form. Now, what's even better, that's just a single bus fault. If I don't select a single bus, if I click in the open area and fault all the buses, there's too much information for the one-line diagram. But now, guess what's on my window? My protective device sequence of events report. It shows me every bus and what's miscoordinated upstream with that bus. It gives me an idea of how much error I could be considering if I have several devices that are impacting my coordination. So it's a very simple thing to do, and some people overlook it, but it's something that you don't want to get in the habit of missing. So that's rule number 6. Mistake number 7. Well, this also applies to a 5-year update. Make sure you're checking your protective device details, the fuses, and matching on all 3 phases, the relay settings, the utility parameters, because they can change, the configuration scenarios that require specific labels, and then any gross load changes you've had as far as the equipment itself. Number 7 is not excluding the main breaker. In the data collection description of 1584, it describes the data collection process of assessing the maintenance condition of large or poorly used or poorly maintained breakers and consider whether or not they should be included in the study or not. Then further down in 1584, it recommends not including the main if there's not an arc barrier between the main bus and incoming conductors to the main. These are 2 different situations, and the decision to include or exclude the main breaker of a particular bus should be made whether or not there's a barrier between the incomer and anybody working on the main bus. And the reason is, if an arc were to form on the main side, the highline side of the main, it would generate a plasma cloud that could result in engulfing anybody working on the main bus and potentially even propagate the arc downstream. So you might say, well, wait a minute, Jim, doesn't the NEC now require covers over incoming terminals of any panel? The answer is yes. And in the recent edition of National Electrical Code, covers are required to prevent accidental contact with exposed voltage. But small plastic covers or cardboard do not constitute an arc barrier. And so it doesn't even come into the conversation when we're talking about excluding the main. Mistake number 8, using the half-cycle current for arc flash calculations because that's the most conservative approach. Well, in 2002, it was recommended to use half-cycle or momentary current as a conservative estimate of what arcing current would be, or the available fault current would be. But it's a well-known fact that over time, available fault current would change due to motor contribution or generator fall off, or even loads that may be dropped off from devices tripping. Consequently, in 1584, the 2018 version suggests a dynamic assessment of arcing current, and EasyPower refers to this as integrated method. And during the calculations, incident energy will be calculated or integrated using momentary current for the first cycle. During the next 8 cycles of a fault, it will be integrating using the interrupting current or the 5-cycle current. And if the fault continues beyond that, then the 30-cycle current is used for the balance of the time. And this is referred to as the integrated method. So this is something I want to share with you. Now again, the purpose is to identify multiple sources that may have different fault currents, may have different trip times, and make sure that the integration for a downstream protective device is being done with the proper amount of current, with a more reasonable assessment of what the actual current is. So if we look at this particular bus and look at the arcing current or the fault current, we can see that the utility supplies 23,000 amps and the generator supplies 4,000 amps of fault current. And they will be tripping at different times. So if we look at the instant energy and we look at how it's being made, we see that the relay is tripping on the generator is what the time controlling the time, but the instant energy or the fault current is much higher. So this is due to be using momentary arcing current. This is set in short circuit options, the arc flash hazard tab. And if we select the integrated mode, EasyPower will assess what the arcing current is at the 3 different thresholds, at 5 cycles, 30 cycles. So during the first cycle, it will integrate using half-cycle current. During the next 8 cycles, it will integrate using 5-cycle current. And during the any balance of the fault, it will integrate using 30-cycle current. So if we apply this, we see we get a much more manageable 11.3 calories exposure for the lifetime of the fault, which is still to the life or the trip setting of the relay. But if you'll notice, it reflects the actual contribution from each side. So if I open this bus up, we see that our utility is supplying 1.3 calories of incident energy. If I put the generator online, it supplies 10 calories. So a more accurate result is going to be the summation of those two, not using momentary current for the whole time limit, the life of the arc. So the question comes up, does that mean that there's a more precise arc flash result? Well, not necessarily. The IEEE refers to arc flash results as estimates, and so they shouldn't be taken to 6 decimal places. I think it's more accurate to say it's a less conservative result by using integrated method. The 2018 model better fits the test data and reduces the conservative guard bandwidth that was built in the original model. So it does suggest that it's more accurate we do in data collection, it will result in a more beneficial or less conservative instant energy calculation. Mistake number 9. I still want to put a hazard risk category on my labels. My safety manual is based on HRC. All my PPE is labeled with HRC. Even the contract electricians are trained to use HRC tables. Why change? Well, back in 2012, the procedure included looking up the PPE based upon the instant energy calculated on a table that was referred to as the HRC or hazard risk category. As a result of the guard banding that was involved, it very often required much more PPE than was necessary for a specific task. And as a result, it discouraged the use of PPE, and the result was counter positive of what we were trying to do. Rather than more safety, we were actually encouraging people to ignore the results. So with a more accurate model in 2018, the industry pressed to gauge the PPE level with the calculated instant energy. So workers were not being trained at the time to understand the PPE rating was determined by the instant energy calculation. And so in 2015, it changed so that the PPE can be determined by instant energy calculation or a lookup table, but not both. And there's still some wiggle room for people that want to define their own category table, just don't refer it to the HRC nomenclature. So the recommendation is try to align with industry, because we're migrating to more and more standardized results, or results that can be equivalent, considered similar to other facilities with the same criteria. As a result, we're recommending, EasyPower is recommending a standardized label with slightly less information as one solution. Another is to make information available to people with scanners, QR scanners, and be able to provide more information as needed to the field personnel working on the equipment. It's important to recognize that compliance with NFPA 70E is not a one and done event. It requires a continuous process of improvement, and part of your electrical safety program should include the ability to accommodate change either in the standards or in your equipment, or in recognized whether or not your original approach was adequate for improved safety of the personnel. So the resulting system should be recognized that modifications will improve safety personnel in your plant. The recommendation is to set a timetable to achieve alignment with NFPA 70E, update your safety manuals, decide between site-specific or energy level to determine PPE, and then train the workforce to recognize which PPE is required for any recognized task. Another label mistake was we put maintenance mode information on the label. This is not a good idea. This is one of those things that it may be at first glance something that makes sense, but it doesn't for a number of reasons. And let me just kind of show you why. If we look at an example here of maintenance mode is a capability built into, due to modern technology, built into most low voltage power circuit breakers that let us control the set points for instantaneous trip based upon either a switch on the front panel of the breaker or on a control line that's controlled somewhere off in the utility room. And what it allows us to do is when we go to short circuit and fault the downstream bus is to invoke maintenance mode and temporarily reduce that exposure for the purpose of doing localized maintenance. And then as we're through removing the maintenance mode control system as we've completed the task. The problem is if we have this information in fact, I'm just going to do the whole system. Let's fault every bus, apply maintenance mode to everything. If we have the information on the label and somebody's not trained to understand or even use the work permit process, they may make a mistake on either the implementation. At the very least, they can disrupt the coordination of the process, because one of the downsides to maintenance mode is that you can make an upstream device sensitive to a downstream fault, and in case of an accident, over shutdown or over discharge excess equipment that may not be necessary. So the bottom line is the maintenance mode discussion is invoking it, utilizing it, and its effect on PPE is part of the work process, the work permit process, not something that should be on a label. That's my opinion. So again, label information doesn't authorize hot work. The place for maintenance mode is the hot work permit. Now, this is something that affects seasoned veterans doing arc flash. I've run into people having the issue of not being able to locate the correct overcurrent protection for mitigation on complex systems, especially when they have a low current source that doesn't necessarily trip on every fault. And you see this in alternate renewable energy applications and in others. A recent exchange involved the question, hey, how come when I'm adjusting my relay that's set to trip at 1800 amps, it's not affecting my arc flash instant energy? And so here's where we stand with this one. This was kind of fun for a number of reasons. So I got the one-line diagram sent to me and identified the bus that was being protected by a relay that's set for 1800 amps. If I go to short circuit focus, fault this bus, we can see we have huge incident energy. And if I look at my arc flash hazard report, I can see that in fact that relay is not tripping. Something called 9005 1.1 is tripping. So it leads one to believe if I look at current on this bus, that sure enough, it's a 4000 amp fault. This relay set up correctly, so what's going on? Well, the first thing I want to do is find this 9005 thing, and to do that, we go out and look for it. So we're going to find 9005, and I see a -1 is a fuse, and sure enough, if I look at the current on this fuse, it's still drawing 9 amps, and who knows what it's being powered by. Once I take it out of the circuit by opening that breaker, then I can go back to my main bus and look at my instant energy. And sure enough, it's down to 7.7 calories. So if I kind of trace back upstream from that breaker or from this fuse switch, I notice that the current is being supplied by a generator of some sort. And sure enough, here's a generator that's on an ATS, but it has backfeeding into my bus. And if I look at my remote voltage from a single bus fault, I can see I have a continuous supply of 360 amps out of my generator. So making that correction solves the problem. I thought that was kind of fun, unique. Now, the issue ends up being, if I go back and look at the main bus, well, wait a minute, this is a 25,000 volt bus, so it doesn't even count. It doesn't even remain in the scope of IEEE. In fact, if I'd been a little bit more observant, I could see under comments that this is outside the range of 2018 IEEE 1584. So that brings us to the question, where is this calculation being made that's giving me 7 calories? Well, if I look at my short circuit options, my arc flash hazard tab, I can see that under advanced, I have checked voltage exceeds IEEE maximum. Then we're going to use the Ralph-Lee method. So that's unchecking that will probably make a difference. And sure enough, it does eliminate the calculations that were being made. But if we even look further into this, if we look at the way this particular main bus is set up, we can see it's being described as an open air bus. And open air, usually at higher voltages, I'm not worried about the three-phase fault. I'm worried about somebody building a single line to ground fault because they're working on an area from a ground or from a feeder, cherry picker. So my question is, how does that dealt with? Well, in EasyPower, if I go to short circuit options and I go to advanced, I can set open air bus to reflect the calculations that are described in NFPA 70E 2009 Annex D8. And this is what's commonly referred to as ARC Pro, a single line to ground calculation. So if I come back here, fault this bus, supply a single line to ground fault, I can see my PPE is actually able to protect the worker at a 0.5 calorie per square centimeter at a working distance of 15 inches. So that solves the problem all the way around. So for those of you that are working in a high voltage, high tension wire environment, that capability is built into EasyPower, and it's under the advanced tab of the short circuit options. And it's by checking the open air, we can provide the recommended PPE for a single line to ground fault. I thought that was kind of fun. Now, as I mentioned, the problem can also be seen where I don't have, when I have a current source that doesn't shut off necessarily into a fault. And that very often happens in PV systems and PV arrays, where we'll continue to have contribution from the arrays, even though the fault has opened up the main breaker to the utility feed. And we talked about the open air bus. So that gives you the top 10 mistakes that I found in the 2022. But wait, there's more. I don't mean to be too cheesy about this, but I think probably the biggest mistake that could be made, and I don't have any numbers on this, so I'm not sure how often this happens, but it's to have a study done and then not proceed with the follow-through that's recommended by the study. In 2018, the cover for NFPA 70E had this pyramid, which is supposed to represent the hierarchy of risk control methodology. And the first thing that's recommended is the elimination, which would be de-energizing, but also engineering controls that would be invoking things like maintenance mode or zone selective interlocking and the like. But the last thing that you should be emphasizing or putting efforts to achieve is putting on more PPE as a solution to a high incident energy situation. So the mistake is not documenting hot work procedures and not making sure that management's aware of tasks involving elevated hazards. A haphazard approach to safety training, and not having an ability to review, audit your systems, and improve the results over time. Thank you all for attending. These are my top 10 mistakes. You're welcome to submit questions via email or at the close of the webinar, and we will answer via email. Thank you for attending today. Have a good day. Stay safe.